So for the second talk, I thought I would talk about a different problem, which also uses hydrodynamics. So motion of a tagged particle. So this is an old problem, but let me get through it. There's a couple of. I thought I would give an overview of some things, and so. So one of the works is with former postdoc Michael Conroy, and the other one is with Vardhan. Okay, so I'll go through a survey of this problem. Okay. Okay. So this is a problem which could be stated for many particle systems, but let me concentrate today on exclusion process. Okay, and so just to remind you from last time, we have a lattice. Let's call it ZD, and there are random walks on the lattice. So this is just a one-dimensional version of it, and each particle has its own exponential clock. When the clock rings, it tries to jump. Let's focus on nearest neighbor. So it tries to jump right or left with probability, let's say P and Q. And if the place where it wants to jump to is already occupied, then it's very polite, it doesn't jump. Okay, so and then the clocks restart. So that's the informal statement of the process. Usually we look at the unlabeled evolution. So we could color each particle and then try to follow, but if we're interested in mass distribution and things like that, then it makes sense just to look at whether a location is occupied or not. And in that case, eta is just the configuration which tells you which lattice points are occupied and not. So in one dimension, this is just a list of zeros and ones. Okay, and so infinitesimally, this could move over, and so this list of numbers or configuration would change, update to this one, where this particle has moved over here. Okay, so infinitesimally, that's what's going on. Okay, and so we'll get to the tagged particle in just a minute, but things are different whether the jumps are symmetric or not symmetric. Okay, so in the case P of 1 is equal to a half, then we have that okay, so I'm introducing some scaling. So in this picture, things are unscaled, but if you make each grid the bond length be 1 over n, so that's what's meant here, and you speed up time. In this case, each particle is sort of like a fair random walk, so diffusive scale seems to be the right scaling, and so this will converge, let's say in probability, to this. So this is what we mean by the hydrodynamic limit, and so you'll get some sort of density here. So I should have said the initial condition. So the initial So let's distribute according to one of these product measures. Okay, so where okay, so rho naught, could be a continuous function, and so something one dimension looks like something like this. This is rho naught, and so at each point you put a particle with probability according to this level at x, and then not with the complement probability. And you do that independently. So if we start with this, so this would be a microscopic initial condition, and this would be some sort of smoothed out continuum initial condition. Okay, and so as time grows, this will flow to something like that, which we're calling rho tu, and the point and rho tu in this case will satisfy something, some constant here. So in the symmetric case. Okay, so it will converge to the unique bounded weak solution of this equation. Okay, so in the case, let's say let's pick a direction, so it wants to move right rather than left. So in this case, then it makes sense, since now there's a direction. There's a velocity, a positive velocity, so non-zero velocity, so the hyperbolic scaling makes sense. And this will go to same thing, where, and let's say we start from the same initial condition. So where dt rho plus okay, so I guess so you could so I guess I wrote it so I could make it d-dimensional, right? So this is so here we could take the in this case we could just take the velocity if you want to make it d-dimensional, so you could just do something like this. So this is so you have to add over plus minus. So in that case, when there's a drift, okay. So in one dimension, this would be p minus q would be non-zero. So this is, let's call this as gamma. So this is a vector, and so this would be the hydrodynamic equation. This is we'll see later in the talk. Non-uniqueness. This equation has non-unique weak solutions in general. Okay, and there's a physical one, the viscosity solution. Typically, if you add on epsilon like this, and then take epsilon to 0, then that defines a weak solution of this. And so that's the physical one. Entropy, they call that the entropy solution. And so that's what you're converging to. Yeah.
In the first case, it looks like the exclusion doesn't survive to the hydrodynamic. Is that
right? Yeah, that's because we're looking at linear functions. So if you look at fluctuations, then you would see some things. Okay, so this is the bulk mass description, and so one would like to follow maybe a single particle, just color it differently, and it's not Markovian in general because it's influenced by the other particles. Okay, so you can't immediately just follow it as a Markov process, but on some physical sense, we think of it sort of like as a random walk in some sort of disordered environment, and so it should have some homogenization. Okay, so anyway, so here's the notation. We've already kind of talked a little bit about this. So this is a formalization of that intuition of what the process is. It's just written here on one line just to fit it onto the slide. But this is the exclusion interaction. So you must have a particle at x, no particle at where you want to jump to, and then you can update the configuration. Okay. And if you want to now study xt, even though it's not Markovian, of course you can consider all the other locations, and if you put that together, that will be a Markov process. Okay, and so one can write down the generator for that. Here's informally one part of that. So if let's say this is the tagged particle, if it's jumping here, then you would update the location of the tagged particle and also the configuration. Okay, so together you can think of it as a Markov process. Is that okay? Okay. So already last time we mentioned that there are many invariant measures for the exclusion process or zero range process, which are mass conservative. There's no birth or death in the motion. We just move things around. And so there's many invariant measures, indexed by density. And this is a nice calculation one can do if one is new to the subject. You can just compute that the Bernoulli product measures will satisfy the equation of being an invariant measure with respect to that generator, for instance. Okay, so, but there are also other invariant measures, and it's still an open problem to characterize all the invariant measures for all types of jump probabilities in all dimensions D. Liggett's book has some open problems. Okay, all right. So we're going to be mostly focusing on one dimension, and for those who are new to the subject, there's some acronyms for some of these one-dimensional exclusion processes. You have TASEP, where you only move to the right. You have ASEP, where you can move right or possibly right or left. TASEP is a case of ASEP. And then you have the symmetric case. Okay, so I already called this as gamma. Okay, and so things depend on this gamma quite a bit. You already see it here. The scaling is different. Okay, so so let me go through a little bit of some of the results, and there's some even open problems starting from this initial condition. So this initial condition means that we start from an invariant measure where we put all the particles according to Bernoulli with fixed parameter rho independently, but let's just make sure that there's a that there's a particle at the origin, so let's just condition that so that there's a particle at the origin. We'll just call that the tag particle. Okay, so even starting from that initial condition, there's some open problems. Okay, so and you can also start from other conditions, which are also interesting, but let me stick with this for the moment. Okay, and so the first thing is what's the law of largest numbers? What's the velocity of the tag particle? Okay, so this is going back to the 80s, and it's what you might suspect. Okay, so gamma is the velocity of a single random walk, and but the others are present, and so they slow down the motion. So there's this extra factor 1 minus rho. Okay, and since we have hydrodynamics on the board, so if you start from this initial condition, then Reza Hanlu proves that you converge to so you'll converge to this kind of solution of ODE. Okay, so that's Reza Hanlu's result. Okay, so that's the first one. So central limit theorem is next, right? So let's stick with ASEP. So gamma is, so we're in one dimension, so gamma is a scalar. So it's and we're going to, our convention is that gamma is positive, or so this is you get a nice central limit theorem. Okay, so okay, so this is so you get this functional central limit theorem. Okay, and so this is all starting from the stationary state, and I'll mention later if you come out of the stationary state. So what would be something out of the stationary state? So it'd be something, this could be one example, which is very much out of the stationary state. Okay, so you only you start with particles like this, right? So this is very much away from being a product measure, from being a Bernoulli product measure with common success probability. Okay, and so you get some different answers. Okay, I'll mention that later. Okay, so on the other hand, if you're in the symmetric process, then this was perhaps a first surprise. So you have some particles. Okay, and in one dimension is 1, right? So this is cannot go below this one, and it cannot go above that one. So it's constrained between these two particles. And since we're in the symmetric case, nobody is moving much. And so it seems reasonable that one should have subdiffusive behavior. Okay, and it turns out that you have this fourth root scaling, and there are other intuitions going to the fluctuation field of if this is the law of large numbers, hydrodynamics result, but if you subtract this off and then try to scale and get a SPDE limit out of that, there's some intuitions which allow you to see nicely the 1 to the 4th scaling, for instance. Okay, so maybe I won't do that. Okay, but there are ways to understand the fourth root scaling. Okay. So when you're in the mean zero case, oh, okay, yeah, sorry, this m should be a gamma. Sorry about that. Okay, so when you're in the mean zero case, then you also have a functional center limit theorem. This coefficient sigma is not explicit, but it exists. Okay, and there's some properties known about it. Milton has nicely proved many things for long-range jumps as well in this problem. And then when gamma is, when you have a drift and dimension is high, 3 and higher, then you also have a functional central limit theorem. Okay, and an open problem, I have it at the end of the talk, but I can mention it now. It's open, actually, what happens when gamma is not 0, but dimension is 2. So open problem. So start from okay, so this is the Bernoulli product measure, independently put particles with probability rho in 2 dimensions. Okay, and then assume gamma is not 0. So for instance, if you're one case would be maybe you're only allowed to go up or to the right. Okay, so you have several particles. Okay, and you're looking at the tagged particle. So so the problem is to show. So even just one-time central limit theorem. So okay, so this is the scaled random walk centered. So gamma is now a vector. So let me. Yeah, so gamma is a vector multiplied by the scalar. Okay, so divide by square root of t. So this should converge to some Gaussian. Okay, so that's not hasn't been proved yet. Okay. Yeah, it's a great question. So. Dimension 1, so the, I mentioned that the tagged particle is in, you can think of the others as some sort of environment, moving environment. In 1 dimension, things are coming back, and so you see them a lot, and so you might think that's a problem, but 1 dimension, the geometry is there. It's helpful. So that simplifies the problem quite a bit. In high dimension, 3 and higher, the particles, the tagged particle is not seeing the others so many times, and you have a lot of transience estimates and things like this, which allow to do it, and that's a theme also, in high dimensional, KPZ equation, things like this, whatever. So, but in 2 dimensions, it's just on the border. So. Yeah, even that's not known. Yeah, so you could make it symmetric like this, and then this is extra piece. So even that is not known. So you don't have the geometry because this one can move around everybody, and you don't have nice green function estimates that you do in high dimension. That's the belief, yeah. I mean, there's some. I mean, I did compute the variance of this and show it's on scale t. So variance of but the limit is not known. Okay, so anyway, just a word about how, for instance, this theorem is proved. For instance, so this is something that is very very classic, Kipnis-Varadhan theorem. So so if you have a stationary reversible ergodic Markov process, okay, and if you start from the invariant measure, and suppose f is mean 0, you know, f should be in L2 also. And if you if the variance of the you know, this is like the partial sum, right? The integral. If the variance of the integral is on scale t, and if you divide by t, and if you actually get a limit which is finite, then automatically you have a central limit theorem. And this is from basically martingale approximation. So the way this is proved is to approximate this object by a martingale. Okay, and so in the tag particle context, one can write the tag particle using the generator. You just stick this as your function into the generator, and you'll get a drift term which corresponds to AT, which is this, and then you'll get a martingale from the Ito decomposition. Okay, and then this one right here is subject to, if we start with the initial conditions that I mentioned, starting from the Bernoulli product measures, stationary ones. Those are also known to be ergodic. Then you can approximate this by a martingale. And then there's some work to show that this one and the martingale that you're approximating by don't cancel each other. And then you can take a limit. Okay, then use martingale central limit theorem. Okay, so this is roughly how it goes. Okay, so this is a nice theorem. Yeah, and just one more word. You know, this another name for this. This is the h minus 1 norm squared of f. Okay, and maybe some of you have used that already in your work. Okay, so anyway, so let's get to some more recent work. Just to you know, just to talk about it and to discuss some open problems. So I already mentioned the step profile. So one problem would be so if you start from, so this is your initial condition. So let's consider the symmetric evolution. So you see already there's something kind of curious here, because even though the jumps are symmetric, because of the exclusion, this particle could never get below 0. Right, the step extends all the way. Right. So the question is, what is the order of what's the growth of this xt, the tag particle, and what are the limit theorems? Okay, it turns out that it's actually growing like square root of t log t. So if you didn't have any of the other particles, it would be just square root of t, right? So there's an extra log t. Okay, and then the second problem I'd like to talk about is some large deviations work. Okay, and so this is a problem now in the asymmetric system. Okay, so there's a bias to jump to the right. And you can ask, we already know the law of large numbers for where this should be, right? That we already mentioned that before. What if you violate that? how is that achieved? What are the costs of it, of being somewhere where you shouldn't be? Right, just the large deviations questions. Okay, so the second one is we won't start from the step profile, but we'll start from a stationary state. Okay, so let me just go through a little bit about the answers to some of these questions, or some partial answers. Okay, so so let's get some intuition. Okay, so let's suppose that you forget about exclusion. You can also ask the question for independent particles. Right, that's maybe a nice problem to work out. Okay, so each one is an independent random walk. Okay, and so in that case, as things evolve, now things can jump onto each other, right? And so the concept of what we're really after is the lead particle, so the maximum. Okay, so if you want to get some intuition from independent particles, we should try to understand the maximum of the process. Okay, so it's a calculation which I think if you're interested, you can try yourself. It turns out that maybe not unsurprisingly, you get a Gumbel limit because Gumbel comes as limits of extremes. Okay, so already here you see that yt is on the order. So if you bring the at to the other side, multiply by bt, at times bt is square root of t times square root of log t. Okay, so this is log of t, and then you divide by square root of log t. Okay, great. Okay, so this is the theorem that he showed. And then he suggested in this paper that the same limit should be true for exclusion process. Okay, and so he was able to actually show that this combination is tight, but he didn't identify the limit. Okay, and part of the intuition is that in the exclusion process, the lead particle will get ahead of everybody, and then it behaves like an independent particle. Okay, so anyway, so we can verify that indeed the same limit holds. Okay, so before we go to the argument, which you might find hopefully interesting, let me get to Tracy Whittam's result, which is also very interesting. Okay, so we're starting from this step profile, and so this is now PQ. Okay, and P is bigger than 1/2, so there's a drift to the right. So this one, it's not too hard to believe that the velocity of the lead particle is P minus Q gamma. Okay, and that's what we have in the numerator. So if you center by that velocity, then indeed it turns out that it should be diffusive. So you're scaling by square root of t, but the limit is not normal. It's a non-normal law, which is kind of curious. Okay, all right, and so the interpretation is that although this one is getting ahead of everybody, in terms of fluctuations, it's feeling the other guys. Yeah.
Intuition wouldn't work in this case, is that right?
Which one?
Horatio's intuition treating particles as independent.
Yeah, it's So the Aratia case is for for fair random walks. It seems that Aratia's intuition works, and for unfair random walks, it doesn't work. So you could think this is another. You can think of this as some sort of I don't know. Maybe it's not. Maybe it's not a good analogy. It's some sort of extreme distribution for this process. Gumbel would be what you get for exclusion if it's fair. But maybe that analogy is not quite correct. Okay, but anyway, in this case, this is also a calculation which any of us can do. So in the case, if you start from the step, but p is less than a half, then you understand that you may go a few steps, but then you really want to come back, right? So the displacement is order 1. And one can, so without scaling, it's order 1, and one can actually compute this distribution. Okay, so anyway, getting back to the fair case, here's a construction of the symmetric process. Okay, so we're starting from the step profile. So you can think each bond. So the dotted lines are Poisson processes between the bonds. So each bond has a Poisson process, and so these are the marks of the Poisson process. And so what you do is you can go up in time, and when you hit a mark, then whatever value is here goes there, and whatever value is here goes here. And so this would, if you just think a moment, this corresponds to rate 1/2 moving to the left, rate 1/2 moving to the right, and if both locations are occupied in the evolution that we described, there's no movement, but there's also no movement here also. So this is another way to understand the process. And so at this time, if I've done it correctly, this is what you get. Okay, and the advantage of this is that if you look at what this particle is doing, marginally, it's actually a fair random walk. The joint statistics are dependent, but marginally, each one of these stirring particles, if you like, this is called the stirring representation, is marginally like a random walk. Okay, so let's try to find the. So we said square root of t log t is the scaling. So how to find that? So let's look at this. Okay, so let's say that it's actually z of t is typically the typical scaling. Okay, we want to figure out what it is. So let's just count how many of these stirring particles or exclusion particles is beyond zt. Okay, that's what we're calling nt at time t. Okay, and so since if the tag particle is beyond this level, that means that this sum has to be at least 1. So if nt as a random variable is of order 1, then that sort of signifies that whatever zt we choose is the right zt. So let's go ahead and take the expectation to see its order. And now we use that marginally each of these stirring particles. So CLT is the location of the stirring particle which started at minus L, or rather at L. L is already negative. L, and then at time t it is gone somewhere. Okay, and so if all of these, so by using translation invariance, just so this has the same distribution as a random walk starting at 0, but minus L or plus L. Okay, and so if you just go ahead and put everything in terms of a random walk starting at 0, but bigger than minus L, you bring it on to the other side, and then you add up. That just gives you the expectation of this, and we want this to be order 1. And now you know that this is just a single random walk, and now you can just analyze it using random walk estimates. And it turns out that square root of t log t will give you that this is order 1. Okay, and if you do a more refined analysis, AT and BT are what we had before, then the limit of this quantity is this explicit constant e to the minus x. Okay, and so that already tells you that from this relation that we have the tightness that Aratia mentioned, but moreover, we can go further, and so this is part of what we were doing. We show that it actually goes to it's an order 1 random variable, so it's a random variable supported on the integers. So it actually converges to this Poisson distribution, and so remember ZT is this combination here. So if you unpack that, then it corresponds to this, and the probability of the Poisson being 0 is just e to the minus whatever the parameter is. Okay, and so we get the Gumbel from that. Okay, so the question is how to show this Poisson limit. Okay, and we have a couple of ways now, but let me go through the old way, which I think has some interesting points, which if one is interested in the exclusion process, it might be useful. So it turns out that the symmetric exclusion process has this very strong negative association property. Okay, and I'm going to say what it is in the next slide. Okay, so a consequence of this property is that if you start from a product measure, so this is a product measure. So it's just delta point masses to the left, and then delta on no particles to the right, product of those. Okay, so this is a product measure. Initial is a product measure, and so if you start from a product measure, then you take any set B. It doesn't have to be Z. It can be ZD. We're focusing on Z. Okay, or any graph actually. Take any subset of Z. Then if you look at the sum of the particles on B at time t, that's what the left-hand side is. That has the same distribution as a sum of independent Bernoullis. So remember, the e to t is a Bernoulli random variable, but they're all correlated. Right? Initially, you start from product measure, but then they're all going to mix up. Okay, so that's a consequence. So if you have that, then you can do a lot of things. And so let's keep that in mind. Let me just mention the strong Rayleigh definition. So it's about this sort of generating function. Okay, so x is indexed over the lattice, and you look at this expectation of this product. Okay, and so strong Rayleigh means that this function should satisfy this differential equation, differential inequality. Okay, So strong really means x can be anything in RA. If you just had Rayleigh, it would be just the positive numbers. But anyway, there's a nice paper by Robin P. Mantle which discusses there's a whole hierarchy of being negatively associated, and strong really is one of them. Anyway, but so as an example, just to unpack this definition, if A is just 2 points, and you choose x as 1, 1, then you see that this second derivative is the left-hand side, and the right-hand side is this product. This will be just 1. This factor right here, if x is 1, 1. So this is so you see that the usual negatively correlated definition is part of this. Okay, anyway. So, all right, so once you have this strong really in hand, then, we're going to go back. So, we were looking at this capital NT, which is, which is this, this is our set which defines B, and so we can rewrite it in terms of independent Bernoullis. So I should say we don't know the means of those Bernoullis. We just know that the sum has the same distribution. So I don't know the distribution exactly of the zeta j. But just to go from binomial to Poisson, you want to show that the sum of the squares of the first moments goes to 0. This is part of how you prove binomial to Poisson. So we want to get a handle on this, and so we go back to the original exclusion process, and this difference would be corresponding to exactly this sum here, and this, in terms of the exclusion, is this also. So this is actually equal to this whole right-hand side here, and so we want to show that that goes to 0. Okay, and so this is a very messy computation. It involves the Stirring representation, some duality, some little tricks. It depends on being the exclusion process. And so an open problem, which I'll mention at the end, is how do you do this for a more general interacting particle system? Okay, so we're able to show that that these things go to 0 and therefore complete the Poisson limit theorem. So is that okay? Any questions about that? Okay, so let me go on to the next one, and we can come back to any questions. Okay, so here's the second question. Okay, so we're starting now in asymmetric exclusion, and now the initial condition is this stationary one. Okay, and so our question is, this is where we should end up. We should be over here, but suppose that we're over here. Okay, so then, so what's the cost of that? So this large deviation question. Okay, so so in some sense, some of this is already known for TASEP. So that means that you're only moving to the right. Agreed? So for TASEP, it turns out that the tagged particle location, when you start from this stationary initial condition, is itself a Poisson process. Okay, so that's I'll discuss that in the next slide. Okay, in ASEP you don't have exact distribution of xt, but Ferrari and Fontes, they showed a nice approximation. So they can approximate the tag particle position at time t by a Poisson process plus an error, and the error has very strong as an exponential moment. Okay, so actually this is an open problem also. So I mean, they proved the result, but I think Pablo himself would admit it's spread over 3 papers, and so there may be some other way of proving this. Okay, so anyway, let me, for those who are interested, let me go through why the tag particle in TASEP is a Poisson process. That might be kind of fun. Okay, so here's our initial picture. So we've distributed particles according to Bernoulli product measure. Agreed? Okay, here's our tag particle, the one in orange. And this is in TASEP. So this particle never sees these particles. It's only jumping to the right. So let me just remove all the ones behind it. Okay, it's the same process. Okay, then since I'm starting from Bernoulli rho, that means that the gaps between this particle and this particle, this particle and this particle are independent geometric random variables. You just keep, a gap is a failure, and a success is when you get to a non-gap. Did I say that correctly? Yeah, okay. Okay, so that would be geometric 1 minus rho. Okay, I think, I think there's many definitions of what being geometric is, but I think it's clear what I'm saying. Okay, so it's geometric, agreed? Okay, so okay, now what you do is you look at the gaps between them, okay, and let's just stand them on edge. So from here to here, the gap is 1. So I have 1 particle, 1 gap. From here to here, there's no gap, so there's no circle. And then there's 2 gaps, so I have 2 circles. Agreed? Okay, and so when this one moves over 1, this gap, goes this way. Okay, and so the gap process is actually a zero-range process. Okay, and the G is the zero-range process. It's the G is you have to have at least one. In order to decrease the particle number, you have to have at least one of these circles. So it's just a rate 1 process. Okay, and so this is going into some. You can think of this as a reservoir, and so you can think of this as being like infinite number of particles. This is just joining them. And now let's just time reverse. Okay, and so let's reverse time. And so if you compute the adjoint, which will control the evolution of the time reversal, then from the reservoir, you are coming in according to a Poisson process with rate 1 minus rho. That's a computation. Okay, so that's something that I will just state. It's not hard. Okay, and then the other guys are going this way. Okay, and so the departure process, so the number of particles which cross from 0 into the reservoir up to time t, that's the location of the tag particle. That's how many gaps have been eaten. And that's the same by time reversal as the number of things arriving, statistically. But the number of things arriving is a Poisson process. Okay. So anyway, if you accept that, then in TASEP, you already know the rate function. So this is a Poisson process, and so the large deviations of this, this is the typical scaled. We're scaling by this is the hyperbolic scaling, which is typical for asymmetric system. In that scaling, we already know the large deviations. So this is this rate function, which so this is the relative entropy of one Poisson to another. So x is Poisson with this parameter, but we want to get to here. So the way to get from here to here is just to change its parameters so that the rate is a. So so this is the relative entropy of one Poisson random variable with parameter this with respect to a Poisson with parameter a. So that's a nice computation. Try that. Okay, so this is the explicit rate function. Okay, so in TASEP, in ASEP, the Ferrari-Fontes relation is not. It doesn't allow. Unfortunately, it doesn't allow to get the large deviation rate function. Why? Because if this were independent of that, then near the zero, you can actually get the rate function. But since they're correlated, you can only get bounds. Okay, so so the question is, what are the rate functions in ASEP? Okay, and how to understand the question also that I mentioned at the beginning. How does the process? How do the other particles organize themselves to allow the motion from here to here? Okay, so even for TASEP, that's an interesting question. Okay, so same problem in symmetric case was handled some time ago. So let me not talk about that. Okay, so let me start with the upper tail. Okay, so upper tail means deviation is more than the mean. Okay, so upper tail means that you're either you're displacing here or here. Okay, and I just put it into two regions. One beyond gamma. Gamma, remember, is the typical velocity of a single random walk, and this is the mean, scaled mean, the velocity. Okay, so I may actually do the argument for TASEP so as to conserve some parameters. In TASEP, as I mentioned, we don't really care about the particles behind zero, so I can just remove them if necessary. Okay, so the answers. So you can ask, what is you can ask before you even start, you can ask, is the Ferrari-Fontes approximation? If you just ignore the error, do you get the same answer? Is the rate function relative entropy of two Poissons? Okay, so it turns out that in this regime, the one closer to the zero, the typical velocity, the answer is yes. Okay, so you actually get the Ferrari-Fontes, what is suggested by Ferrari-Fontes approximation. And on the other hand, for a bigger than gamma, then you get something a little bit different. Okay, and the reason is that in TASEP, you always get the relative entropy of two Poissons, but here the reason is that, and I'll go through that also, is that if you're deviating to here, then there's no way that a tag particle has any chance of getting here without changing its rates. And in ASAP, there's a rate to go right and a rate to go left, so there's two rates to change. So in ASAP, you can think of the tag particle as being some sort of birth-death process. And so there's two parameters to change, and so you'll be changing a birth-death process rather than a Poisson process. Okay, and anyway, this will reduce to the TSEP 1 when gamma is equal to 1, for instance. So that's something that one can check. Okay, so let's look at this regime. Okay, so there's some constraints. Okay, so of course, for the tag particle to get there, the particles in between have to move faster or do something. On the other hand, if you have a lot of particles in between, then that's a very costly proposition. To speed up each particle is to change its rate. To change its rate up to time, macroscopic time n, would be a cost of order n. But if you have order n particles, then you'd be getting a much larger rate than what we expect. So the alternative is to since we start from the stationary initial condition, because it's random, right? So we're starting from this initial condition. So since it's random, we can, so we're in some sense doing annealed large deviations. We can change the initial condition. So we just change the initial condition. If there are too many particles in between, we just remove them. So here's the intuition. Okay, so here's our tag particle. This is the scaled picture. Okay, so this is the macroscopic picture. So our macroscopic tag particle starts at 0. Okay, and this is the typical density profile. It's flat with parameter rho, but we will just make it empty up to some interval, and the idea is that the particle that's right here will get to A at the same time now that the changed tag particle will get to A. So there won't be any impedance in the motion. That is our suggestion for how optimally you achieve this rare event. Okay, so to see how this picture is derived, so finally, hydrodynamics is involved. Okay, so there are three ingredients. The hydrodynamics, which we've already discussed a little bit. There's this current relation and the super exponential inequality. Okay, so this is our slide for hydrodynamics, which we've already put onto the board. Okay, so we have hyperbolic scaling. This is just to remind us what the hydrodynamics is, and we'll be converging to the solution of this equation, which is the physically relevant one, the entropy solution. Okay, so that's hydrodynamics. Current relation, if the tag particle is beyond this level, so let's just do TSEP, okay? So if your tag particle is beyond A, that means that remember, I can remove particles. So right, so here's 0, and here's an. So these particles. Let me do the argument for TSEP. Okay, so I can just get rid of these particles, right? Because in TSEP you don't see them. So here's our tag particle. So if this tag particle wants to get beyond an, that means that all of these have moved also beyond. And and since there was nothing behind, this is the same event. Okay, so you're saying that there are no particles below an at this time, Tn. Okay, so that's the same event. Okay, and for A sub, there's a similar version of this in terms of current. So this is a very simple, but I thought this would be easier to see. Okay, and let's now try to go to this thing. You can call this a height function if you want. The integral of the density has some nice, maybe some possibly nicer properties than the density itself. Okay, and so if we integrate the density from 0 to x, let's call it h dx. Okay, so this relation here, which is macroscopic, if you divide by 1 over n here, which you can do, right? The right hand side is 0, 1 over n, then 1 over n this is the same as the height function at a, approximately, if you believe hydrodynamics. Okay, and so the height function at a being 0 is signifying that the scaled tag particle has gone beyond a. Okay, the advantage of going to the height function, you can stick it back into the hydrodynamic equation, wherever it is, this one, and you can get this this equation for the height function. And the advantage is that the height function satisfying such a conservation law has a variational representation. Okay, and so that's part of the advantage. Okay, so I can solve. So even this has non-unique solutions. And this will have an entropy physically relevant solution. So the physically relevant one satisfies this variational formula, the Hoflachs formula. Okay, and this function g is explicit. It's the convex dual of u times 1 minus u. Okay, so let's get to the third ingredient, super exponential inequality. So we mentioned that if you have to move many particles, that's costly. So this is an expression of that. So you're saying that the particle number beyond an can't you can't move more than what you typically expect in the hydrodynamic flow. Okay, rho is the entropy solution. Okay, and so this exceeding that will have super exponentially small probability. Okay, so another way to say that in terms of the height function is this thing here. Okay, so if this was going on things beyond an, by mass conservation you can translate to things below an, and so that corresponds to the height function, and so you get this relation. So the okay. All right, so let's just combine all these ingredients. Okay, so we want to move to let's just take time t equals to 1. Okay, so we want this to be close to a. Okay, so the current relation said that the number of particles below an should be 0. Okay, this quantity by the super exponential inequality, this thing here. So this is a small event. So this typical is this inequality. So we should have that this is bigger than the continuum height function, so this value is 0. Okay, so from the variational formula, you just now play around with it, and so this is true for every z. So in particular, this is less than this explicit function. Okay, and here's I just drew what g was, and so remember h0 of z is the height function initially. Okay, so yeah, so so in the variational formula, this is the height function of the initial. So this is the integral of the initial density. That's what h0 of z is. Okay, and so this is giving you some bound on the initial density. Okay, so the initial density has to satisfy that it's less than this g function. Okay, and the g function is 0 here, and it's looking like this here. So you get this, these relations. If you differentiate this, you should get back the density, and then that's the picture that we mentioned. So this tells us the continuum density, what it should be, and so we would say that microscopically we start from this this measure, sometimes called local equilibrium measure. Okay, and that's the picture that we drew before. Okay, so the blue line is the rho naught that you get from this equation, and if you now flow the PDE, what's happening is that the blue line is going to this step, and so there's some work to show microscopically that the particle starting here gets over here, but that gives enough room for the tag particle to move, the red dot. Okay, and so there's a cost, right? So you want to change from the dotted black line to the blue line. So it's a cost of changing Bernoulli product where the dense parameter is the same to this one. That's a calculation, and if you scale it, you get this answer. Okay, and then in TASEP, you're only moving to the right, so it's a Poisson process. So we change it from rate 1 to rate A, and this is the cost of that. If you add those two, you get back the answer that we already knew. Okay, so this is one optimal way of achieving. Okay, so we don't show it's the unique optimal way. Okay, in ASEP, you're going left also, and so you have to change the rates P and Q. So in that same regime, you would change a birth-death process to a different birth-death process. So you would be changing P to PC and Q to Q over C, and C is this. It turns out that this is what we should change so that we get to A. Okay, anyway, so that's the upper tail. Okay, so okay, so let me just mention. I think maybe we're getting late, so maybe I won't go through everything. So okay, you can ask in the lead particle work. So if you start from this step profile, how many of them do you actually need for you to actually get the same Gumbel limit? Right? If you only have a finite number, you're only going to get normal distribution. Right? So it turns out that this is something like t over log t. So that tells you that this one is not influenced by anything after t log t. Okay, so we can show that. Lower. Sorry? Yeah, this thing that we did before. So xt over bt minus at. So to get that same limit, but if you start with maybe this configuration where it's empty to the left after some number of particles, so you're considering an array. So you're considering at each time t to have some increasing number of particles. But if they're of order t log t, then this one is still being pushed to the right, and you get the same limit. Yeah.
You could also imagine deleting like every fraction of some particles on the left, trying to figure out what fraction you should delete to get the same double limit. I don't really expect an answer off the top of your head.
So that's a good question. So if you do this, right, and you just do alternating, then you also get a double limit, but there will be, I think, a half here. And so in fact, we can do any periodic step. So and it can be a mixture of random and deterministic points. And the constant here will change. Yeah, exactly. But thanks. In fact, if one is interested in that, so here's anyway. Maybe it's too many technical details. So yeah, so that's a yeah. So if you start taking more and more fraction, then I think it's like k if you every k ones. So I agree. You will be thinning out, and so there is some sense. We haven't done that limit where you do k with t. That might be interesting. Yeah. Sorry.
What if you take the second? Don't take the
Yeah. The second one. So the second one. So this is so the second one. So this is the same as this, right? This is and so when you do the limit, you're looking at Poisson of 0 or 1 for the second. So you'll pick up the this is the Poisson probability of 0. You'll also add to that the Poisson probability of 1. And so you can go back any number. And so in fact, we haven't done it yet. We're talking about it. We should be able to get the Poisson limit, the Poisson process limit. So if you look at so if you add these guys up, then this should converge to a Poisson process with intensity e to the minus x. So what we haven't done yet is, so to do that, you need to show that if you separate into two pieces, some asymptotic independence. We haven't done that yet. Lower tail, we can do some. Lower tail is interesting. Okay, so why don't we go to that? Here's the open question that I drew over here. Okay, let's go to the lower tail. Lower tail is interesting because it's much more open and it involves things that Morrow considered a long time ago. So I'd like to mention that a little bit. So let's do a case. Okay, so this is so if you have just a little bit of patience, let me just take 2 minutes and go through this. Okay, so suppose that A is 0. What does that mean? That means that you're not displacing at all. Okay, so we're back to the large deviation problem. Okay, so oh goodness. Okay, so we here's the tag particle. So a is equal to 0. So this may move 1 or 2 spots, but on the hyperbolic scale, it doesn't move. Okay, so one way to achieve that is just to make sure that the clock doesn't ring. Okay, so that's one, but we already know the answer. If you go back into the rate function of TSEP and you stick a equals to 0, then the answer is actually 1 minus rho. So this is too large. This is not the right strategy. Okay, so another way is, everybody knows you're in traffic. You can't move because there are people in front of you. Okay, so the question is how much should you block by? So if you block by size n microscopically, right, then the evolution of this, if this is your initial condition, then you're coming back as a rarefaction wave. Okay, and so this will come back to here in time 1, and so you might think that's the way it actually is achieving this, but if you actually compute the relative entropy of Bernoulli, where you have this success probability and then the usual one over here, the relative entropy cost is minus log rho. That's bigger than 1 minus rho. So that's also not correct. Okay, but you can actually block with less particles. So you just block up to rho. Okay, and then you ask, how are you evolving? You're not evolving by a rarefaction wave. If you did, this would get here before time 1. So what you do is you maintain the shock. Okay, and so there's a shock speed which you can calculate. It's minus rho, and then you maintain that shock. So that means that this thing is moving at speed minus rho, velocity minus rho this way, just like this. Okay, and that actually is a weak solution of the hydrodynamic equation, or wherever it is. Okay, so that's a non-entropic evolution. Okay, so typically what should happen is a rarefaction. Okay, so another way to understand that is, okay, let's go to particle hole, right? In exclusion, particles, you can think of them as one type of particle and the holes as another type of particle, right? So you can also look at the dynamics of the holes. That's also a way to calculate. So if you fill with particles here, that's the same as having no holes. And if you fill with particles density rho, that means the hole density is 1 minus rho. Okay, so now the same question is, now the particles are moving to the right. That means that holes are moving to the left. Agreed? So this lead hole is going to, you're asking when does it come back to the origin? Its rate is actually rate 1. With rate 1, it's going left. Okay, but if you change it to rate minus rho, then it will get to the origin at time 1. That's the same as changing a Poisson process with rate 1 to a Poisson process with rate rho. And that has this cost. If you now add to the profile cost, the cost of changing to this or this in the whole picture, if you add those two together, then you actually get back 1 minus rho. So that's one way of achieving the right cost. Okay, so you can do the same thing when a is between 0 and rho. You do this kind of thing. So, and then there's a way to think about that as well. Another way, which also has tons of open problems, is to go to the large deviations of the empirical measure. Right, so this is law of large numbers. So you can also ask about large deviations, right? So in the asymmetric case, there's still open problems. So this was considered in Jensen's thesis Vardhan has a write-up of the thesis in 2004. There's another student who wrote a thesis in 2008. Recently, Costel and Tsai has some work on this, where they considered height functions and did it by integrable probability methods for TASEP. Okay, and Morrow, in his thesis, also considered this problem in a different model. Okay, let me say that maybe this is the end of it. Okay, so you can actually compute, so enough is known that you can compute the cost of the process evolving to a different, the cost of this object evolving to a different density. If the evolution, if you're evolving to something which is nice enough, and this is a nice enough evolution. This one going back, that's a nice enough evolution, and so that's another way you can actually compute the process cost of evolving to that density instead of the one, instead of just being under stationary. Okay, and so that will give you another way of computing all the numbers. Okay, so what's open is we don't have it for ASEP. So this is all for TASEP. Okay, so there's no statement at the moment of large deviations of empirical measure in ASEP, which is not TASEP, for instance. So that's a nice open problem. And because we don't have that, we don't have a full understanding of what's going on for the tag particle, for instance, in even this problem, in the lower tail. Okay, so this is kind of fun. Current is related. Morrow talked about current yesterday. So this is a number of particles which cross 0 from the left and go to -1 from the right up to time t. So the number of things which cross the bond. And some of the work that we discussed can apply to this if we start from stationary initial condition and the density is not half. When the density is actually half, then the integrable probability technique probably is the way to go. You'll get some Tracy-Widom type stuff. Okay, so I think that's it. Thanks. Yeah.
There's some results about the generalized exclusion process that should allow those K particles.
Yeah, that's a great question. So in fact, yeah, we for the lead particle we can do that. So if you start with some number, so let's say K exclusion. So you can have at most K per site, right? Symmetric. So the rate is eta of x K minus eta of x plus 1. So this will be the process. There are actually many types of K exclusion process that you can consider, but this is the one that we can do it for. Okay, so this is the one which corresponds to each particle having its own clock in some sense. Okay, and so for this one, if you look at the maximum, now it's not tagged particle, it's maximum, then you'll get a Gumbel limit. Same sort of limit, the constant will vary. Okay, and so we can't use the strong Rayleigh property because it's not known. So what we do is we use something older. There's some notion of monotonicity which is already in Liggett's book, and that was proved for K exclusion by Radig and co-authors. And so we can use that And then to get the Poisson limit, since we don't have the Rayleigh identities, we just do it by factorial moments. Okay, so that's being written up at the moment. In the exclusion one, that's a nice question. So so other number one could also apply to the tag particle result. So in the number one, even for suppose you had zero range, I'm not sure exactly how to do that. Okay, and even large deviations. Okay, so maybe some types of zero range, maybe this is possible. Okay, and anyway, so some questions.
Is there any chance to do this kind of computational asymptotic law of the fluctuation or deviation for the particle using integrable representation like Castell and collaborator did for many legislations?
Yeah, that's a great question because it's not an easy representation in terms of height function. I guess in principle, you can do it, but it'll be a very complicated event. On the other hand, the Tracy-Widom result is you want to start from a step profile. Even in Quastel and co-author work, you must have a lead particle and no particles beyond it, right? So if you want to start from stationarity, you might ask, is that a problem? It's not completely a problem. Why? Because if the tag particle is here, we know that particles over here don't really interact up to time t. So you can just throw, you don't have to worry about them. Okay, and same thing on this side. Okay, and so there are beta ansatz, integrable probability, Jeremy's formula, which tell you how any particle here evolves, involving complex integrals and all these other things. And so there may be a chance to do these things, but I don't know how to do this.
In principle, it's like computations are incredibly long, but on the other hand, one just has to take the limit in these huge formulas.
Yeah, that it might work out. I don't know if it would tell you how you get there. Okay, so okay, so I mean, so so.
What was the integration that produced it?
Yeah. So, but it's a good problem. So actually, if you look at the step profile, if you look at the large deviations of the lead particle, the upper large deviations are the same as if there were no other particles. But the lower ones I haven't computed. I think those that's going to be a different answer, because all these guys are going to be involved. So that one might be doable using the Tracy-Widom stuff as a maybe that's a I don't know if that's the problem to enter if you want to enter into that field, but
For instance, the Tracy-Widom result, you can do it in this way.
it's a formula. You have to scale it and take the limit and do asymptotic analysis. Yeah, I just throw up my hands. So I'm not. Maybe with if somebody is really into it, I can learn something. Maybe Mauro, you're interested in this. We can talk about it.
So the Poisson Gamma cloud result
Yeah.
should be true also for interacting exclusions.
Yeah, that's a good question. So so the building block that we have is that you need some monotonicity. We're using monotonicity, and once you have that, then And if you have some notion of stirring each particle carrying its own clock or something like that, which I think may already not satisfy your process, but so there should be some other more general way of doing this, okay? And so I know some ways of doing it for particular processes. So it's an open question. I'm not sure. Yeah.
So kind of at the end here, you mentioned the situation where you can select the non-entropic
Yeah.
solution at some cost. This is the first time I'm seeing something like that. To kind of test my understanding, suppose I tried to select a function that isn't a weak solution at all. Is that a super exponential cost?
So that's a super exponential cost. So you cannot, so in a hyperbolic particle system, the meta theorem is that you should always deviate only to one of the weak solutions. And it'll be super exponential, and the rate function will be infinite on those others. So that's not the case for symmetric exclusion. Symmetric exclusion, you can add on some drifts. So the way you evolve there is you go from symmetric to weakly asymmetric process, where the jumps are 1/2 plus something. Whichever day it is. You said Thursday next week. Is that right? Okay.